Hi there. Here's my solution to question 3.52. So I have already entered nitrates into list 1, that is the explanatory variable. I have entered the absorbance values into list 2, my response variable. So in part A, we're supposed to determine if the calibration needs to be done again, and we need a correlation above 0.997 in order to determine whether or not that's required. So we should plot the data and look at the correlation. So I've already got my plot set up, so I'm just going to press zoom 9 in order to take a look at the scatter plot, and it is indeed positive, it is indeed linear, and it's quite strong. So to calculate the correlation, we can go to Stat, over to Calculate. We'll choose option number 8. My explanatory and response lists are already specified. I'll hit Calculate. So no, we do not need to do the calibration again because the correlation is 0.9999, certainly higher than what was specified in part A. And in part B, we're asked to write the least squares line for predicting absorbance from concentration. So we already have the intercept and the slope here on the screen. So I have already written that down. A couple of things to remember. When you write that, here is the intercept, 1.66. Here is the slope, times x, times the explanatory variable, and it is always equal to y, but it is not just y, it is a predicted y value. That hat is required. It is also required that you explain what x and y are. So x is milligrams of nitrates, and y is the absorbance. In part B, you're also asked to interpret the slope and the intercept. So the slope I think of as 0.11 divided by 1. So these are both positive. So remember, what these represent are changes in the explanatory and in the response variable. So what's really going on in the denominator, this is the change in the x value or the explanatory variable. So that's the change in nitrates. The numerator is the change in y, that is the change in the response variable, so that's the change in absorbance. So if I were to write this out carefully, for a 1 unit increase, so 1 additional milligram of nitrate leads to a 0.11 increase in absorbance. That's how I would write it out. 1 additional milligram. 1 additional milligram of nitrates leads to a predicted or an estimated or an approximate, a predicted increase in absorbance of 0.11. That's how I would interpret the slope. So for the intercept is 1.66, but remember that it corresponds to an x value of 0. So if you look in the equation, if x is 0, this part of the equation disappears, so your predicted y value is the 1.66. So that intercept says if x is 0, so if we have 0 milligrams of nitrates diluted into this solution, the estimated absorbance is 1.66. That is the interpretation of the intercept. With no nitrates, the predicted absorbance is 1.66. That is the interpretation of the slope and the interpretation of the intercept. In part C, your job is to get a prediction, to create a prediction. So if we have 500 milligrams of nitrates per liter, what would the expected or predicted absorbance be? So it is important that you always show your work, even when it's simple, when you're doing something like this. So I am trying to predict the absorbance. I'm trying to create a y hat value. So here is my intercept plus my slope times the 500 milligrams of nitrate. That is what was specified in the problem. That is my X value. So I can simply calculate that on my calculator. Not too complicated. We'll go back to the home screen. So into my calculator, I'll just put the 1.66 plus 0.11 times 500. This will give me my estimate, my prediction. My predicted absorbance would be 56.7. That's it. So my y hat is approximately 56.7. That's all that part C involves. So lastly then, in part D, do I expect this prediction to be accurate? I should give graphical and numeric evidence to support my answer. So yes, I would say that this prediction is going to be pretty accurate. And let's start with the graphical evidence. There are two ways that you could look at this or consider this graphically. So number one, again, if I zoom 9 this, the relationship is linear, and I have estimated this with a straight line. I would expect the best fit line to fit the data pretty well, and I can actually plot that. If I type the model into Y1, I can put in the 1.66 plus 0.11x, and I can plot the model on top of the scatter plot. So it certainly fits the scatter plot very well. That's one reason why I would expect my prediction to be pretty accurate. Number two, we can look at the residuals. So if I go into my scatter plot, I will change my Y list to be the residual list. Second, stat, and I can go to the list resid and press enter. So zoom 9 that, I can take a look at the residual plot. Remember, the residual plot, what this does, this plot shows me a plot of the errors that are being made. So if I look at this, I don't see much of a pattern. Sometimes the residuals are above the x-axis, sometimes they're below. It looks like these residuals over here are a little bit bigger when the number of milligrams of nitrates rises to, and we could trace it to see what those actually are over there. So right here, I have a very small residual where X is 400. Again, I have a pretty small residual where X is 800. We're trying to make a prediction in this area here where X is 500, and I don't see very large residuals there. The residuals get a little bit bigger over here where the values of X are larger at 2000, but in fact, that's not where I'm trying to make my prediction, and I still don't see much of a pattern here. It is true the residuals tend to get larger as the value of X increases, but I'm not looking at a particularly large value of X. So the residual plot, it's scattered. I don't see much of a pattern. It really doesn't suggest that I'm going to have a problem with a prediction at X equals 500. The last thing to think about then, if I go back to the home screen, I'm going to rerun the regression just because I want to see the value of R squared again. I hardly need to see that value. I know that it's about 99%. So there it is right there. If you take the correlation and you square it, you get 0.9999. So what this says is, again, it gives me very strong evidence that my prediction is going to be accurate. So let's make sure we interpret this value of R squared correctly. So R squared is approximately, well, for all intents and purposes, we'll call it 99%. So what this means is 99% of the variation So 99% of the variation in absorbance is explained by the linear regression on milligrams of nitrates. I suppose if you wanted to get technical, it's per liter of water. So what this is telling me, this is another piece of information that really does suggest that my prediction is very likely to be accurate. 99% of all of the variation that we see in absorbance all of that response variable, 99% of the variation in that response variable is indeed explained by our linear regression or our linear model or the line on milligrams of nitrates using this particular explanatory variable. So again, because I'm explaining so much of the variation in absorbance using this linear model, if I use this linear model to actually make my prediction, again, that's evidence that I would expect that prediction to be pretty accurate. You can expect to have to, on your test, you can expect to have to write a model, explain what X and Y are. You can expect to have to interpret what the slope and the intercept mean. You can expect to have to make a prediction, and you can expect also to have to be able to interpret the value of R squared in context. That makes this a great question to look at for review. Hope this has been helpful.